receiver and station dependent errors. Okay, so among these three, we were discussing on the observation medium dependent. That means when the signal is passing from the satellite to the receiver, it is passing through an observation medium. It is passing through a medium of propagation. That means whatever is coming in between, that is our atmosphere, which again we can divide into two parts, ionosphere and troposphere. So closer portion towards the Earth's surface is the troposphere, and uh, the portion closer to the satellite is the ionosphere. Okay, I'll skip these. So errors due to signal GPS signal propagation are induced when the signal passes through the ionosphere. So ionospheric delay is larger than the tropospheric delay. Ionospheric delay is around 10 to 100 meters of error, while neutral atmosphere will bring about 2.3 to 30 meters of delay, and this also depends on the elevation angle. Okay, so the equations that you see here are equations for pseudo range observable and carrier phase observable. Okay, so these errors due to ionospheric delay and neutral atmospheric delay, that is tropospheric delay, they come in the terms, as you can see, circled ones in these observation equations. Okay, so I refers to the ionospheric delay, T refers to the tropospheric delay. So if we want to get the most accurate position estimate from the GPS receiver data, we have to take care about, or we have to know, or we have to account for the delays caused or the errors caused due to the propagation through these two mediums. Okay, as you can see in this figure, the red line is the signal starting or originating from the satellite, passing first through the ionosphere, the light blue circle, and then through the troposphere, the dark blue circle. You can see how the ray is bending. Okay, it is not a straight line. If there was no medium, that means there was no atmosphere between the receiver and the satellite, then there would not be any refraction happening. And because of this refraction of this electromagnetic signal from the satellite to the receiver, there is some extra distance traveled by the signal. And this extra distance is known as delay, and it is also measured in the units of distance. For example, ionospheric delay we saw 10 to 100 meters, and tropospheric delay 2.3 to 30 meters. Okay, so these are the different um, layers in the atmospheric model that you can see in this picture. We will see a detailed picture in the ionosphere portion. So for tropospheric delay, you have to remember that most of the weather and water vapor mass is contained below the tropopause. So tropopause defines the boundary of the troposphere. From the surface of the earth towards around 10 kilometers of height, we find the troposphere. Okay, so in the atmosphere, there are different layers: troposphere, stratosphere, mesosphere, and these distinction is happening on the basis of vertical temperature lapse rate. That means how the temperature is decreasing, what is the rate at which the temperature is decreasing as we move upward from the surface of the earth. Okay, so this you can see on the right hand side, how that red line is changing, that represents the vertical temperature lapse rate. So wherever it is changing, we have a new layer of the atmosphere. The main thing that you have to remember about troposphere, it is non-dispersive medium for radio frequency below 15 gigahertz. So for our GPS signal, this troposphere behaves as an electrically neutral layer. Okay, so having both the frequencies, there is not much distinction about the propagation characteristics of these two frequencies in the GPS signal because of the troposphere. Okay, so we saw how to arrive at the propagation equations or wave equations. They originate from the Maxwell equations, which define the interaction between the electric and magnetic field and how they interact with the charges and currents. Okay, so the main thing that we arrive is at refractive index n from here. Okay, so if we want to understand the delay, we have to account for the atmospheric refractive index n. So since the values of n are very closer to unity, so we want to make distinctions between different values of refractive index. So for that purpose, we introduce a new terminology called refractivity. Okay, and the formula is given on the right hand side. Capital N is the refractivity and how it is related to small n, that is refractive index. Okay, this usage of refractivity will avoid the usage of numbers that distinguish only very little from unity. So as we discussed, there is a real part of refractivity as well as imaginary part of refractivity. It is a complex number. So real part will take care of the electromagnetic wave refraction. Okay, and the imaginary part will take care of the absorption. So refraction part is taken care or represented by the real part of refractivity, and imaginary part of refractivity will tell you how much absorption or attenuation of the signal has occurred. Um, there is a permanent dipole moment of water molecule, which also causes difference or variation in refractivity in the tropospheric water vapor content. Okay, so we will see how this affects the propagation of electromagnetic waves. So as we saw, there is a dipole component of water vapor, as well as the density of water vapor is also quite varying inside the atmosphere. So what happens is the wet and dry constituents of the atmosphere, they affect the propagation delay of GNSS signals in different ways. Wet means the effect is coming from water vapor, and dry means effect is coming from the dry air containing all the dry gases and aerosols, etc. Okay, the dry part is generally very stable in nature as against the wet part. Wet part varies very dynamically. So it is harder to model the wet part of the refractivity as compared to the dry part. Okay, so in the equation below, you can see capital N is composed of three portions. Okay, summed up together. The first portion is concerned with dry air. Okay, it depends on density of dry air. So you can see the term rho d written. Okay, this portion is accounted for by hydrostatic refractivity. So hydrostatic, wherever the term comes, it means we are talking about the dry portion of the atmosphere. Hydrostatic means the water is not moving in that portion, so automatically it means the dry portion. Okay, so capital N is composed of hydrostatic N plus wet N. That means hydrostatic refractivity plus wet refractivity. Now, wet refractivity is again composed of two portions. One is due to the density of water vapor, as you can see the middle term in the equation, as well as the dipole component of the water vapor. So hydrostatic refractivity depends only on the total density of air, which can easily be deduced from the ground-based pressure measurement. So we only need pressure measurements and the location of the site, as we've seen already in the models which uh, design the hydrostatic delay, as we've seen Sasta-Moine model and Hopfield model. Okay, so what is happening there? We are using the ground-based pressure measurements as well as the site location to deduce the hydrostatic refractivity. While wet part is related to temperature and water vapor pressure, which is dynamically varying and very harder to model. Hence, what is the general trend? We find out what is the hydrostatic part, and then from the total we remove the hydrostatic part to get the wet part. Okay, as we'll see in the next slides. So what is propagation delay? The extra distance traveled due to the refraction is known as propagation delay. So here you can see capital L is the distance from the receiver to the satellite. Receiver means R, satellite means capital T. Okay, so capital L equals to distance, optical distance from receiver to the satellite, and it is an integral of refractive index multiplied by distance. Okay, so what is the delay? Difference between the optical path length as well as the true geometric distance. Okay, so there is a geometric distance capital G, which assumes that there is no medium of propagation, there is no refraction happening, and there is vacuum between the receiver and the satellite. And there is a true ray path, which is the actual distance traveled by the signal, which contains the extra error portion due to the signal propagation in the atmosphere. So naturally the difference between these two quantities will give you delta L, that is tropospheric delay. Okay, as you can see here in the second equation, subtraction of these two quantities is the tropospheric delay. Now when we substitute refractivity inside this small n refractive index, we get the equation like this. So naturally the integration of ds from receiver to satellite will give you capital S. Okay, here this is the geometric length of the true bended propagation path. So capital S minus G will produce the bending effect, while the wet and dry components of the refractivity are modeled inside the first red box. Here we discussed about the relation between the delay and the elevation angle of the satellite. So smaller the elevation angle, more will be the delay. As you can see, smaller elevation angle means even more slant will be the delay, and more slant, more inclined will be the delay. That means more distance is traveled by the signal from satellite to the receiver. So naturally, for smaller elevation angles, as the elevation angle of the satellite is lower and lower, it will cause more delay, while as it is closer to the zenith direction, that means the point directly above the receiver, okay, that will cause the minimum amount of delay. This is known as zenith delay. And all the slant delays at a receiver point are related to zenith delay at the receiver point using a mapping function. So mapping function is given by 1 upon sine epsilon, and epsilon is the hz by capital R. Hz is the height the delay is causing, and R is the hypotenuse here, or that is total slant delay is the capital R. So this ratio is sine epsilon, and 1 upon epsilon is the mapping function. So why are we concerned with the zenith delay and slant delay? So at a point, at a GPS receiver point, there can be n number of slant delays according to the different elevation angles, and when we combine all of these project to one single delay at the zenith, we what are we doing? We are representing a flat homogeneous atmosphere. We are assuming the atmosphere is flat and homogeneous, it is not varying much, so we can reduce the number of unknowns in this case by projecting all the slant delays onto the zenith direction. Okay, so zenith delay, you understand, the true delay that is happening is obviously in the line of sight from the satellite to the receiver. It is inclined, it is known as slant delay, and when we project the slant delay into the zenith direction, we obtain the zenith delay. Okay, so here on the right hand side you can get the whole delay picture. The total atmospheric delay is divided into ionospheric delay and neutrospheric delay, that is tropospheric delay. Ionospheric delay can be removed using dual frequency. We will see how it will happen. While the neutral delay is modeled, the dry part is modeled, hydrostatic part is modeled using the pressure, temperature, refractive index data at the receiver, while zenith where delay is obtained from the neutral delay by subtracting the hydrostatic delay. So you can see 90% of the neutral delay is caused by the hydrostatic delay, while water vapor is only causing up to 10% of the total delay. So for hydrostatic delay, there is a phenomena known as hydrostatic equilibrium, which relates the pressure, density, and gravity. Okay, in a at a height z, and from here you can compute pressure in terms of gravity, and this information you can use in your model to calculate hydrostatic delay. So zenith hydrostatic delay is given by the Sasta-Mon hydrostatic delay model, where if G effective, that is gravity, which is dependent on some geopotential height. Okay, it is a function of latitude and geopotential height. So you only need three information to compute the hydrostatic delay or to model the hydrostatic delay. What is that? First is the pressure information, next is the latitude of the site, and next is the geopotential height of the receiver. So as we spoke about before, the wet delay is difficult to model, hence it is obtained by subtracting the hydrostatic delay from the total delay, as you can see on the equation at the bottom of the page. So ZWD is equal to ZTD, TD means total delay, minus ZHD, HD means hydrostatic delay. So this is how we arrive at zenith wet delay, and the one of the very highly popular tropospheric product is known as precipitable water vapor, and that is obtained by multiplying a factor pi to the zenith wet delay. So what is precipitable water vapor? You can see in this figure, if we imagine a unit area column on the surface of the earth, that column is to be filled with whatever water vapor is prevailing at in the atmosphere at that place. Okay, if that precipitate and fills up this water, fills up this column, that will represent the precipitable water vapor. This is related to the zenith wet delay by a factor pi. Pi is a function of water vapor weighted mean temperature. Okay, so temperature here at the receiver, that is going to be used to compute the factor pi, which is to be multiplied to the zenith wet delay in order to get precipitable water vapor. So mapping function, there are many mapping functions available. So simplest is 1 upon sine elevation, as we have already seen, but this is for a plane atmosphere. It is the simplest form, which is assuming that spherical constant height surfaces could be approximated as planar surfaces. That means we are trying to ignore the bending. This is accurate only for very high elevation angles, but that is not um, always the case. So we need to use a little bit more complex form of mapping function. So since there is a curvature in the earth's surface, we need to have a continued fraction form. Okay, again and again the bending is happening or the curvature is happening, so we will have a continued fraction form of the mapping function, continued 1 upon sine, 1 upon sine elevation, 1 upon sine elevation. Okay? So for this complex continued fraction form of mapping function, there is a truncated, easier form, easier representation, which is given in the third equation. You can see this is defined by, there are two things here to notice. First is the small I. Small I means either mapping function value is for hydrostatic part or mapping function value is for the wet part. Okay, so there are two components of the delay, wet and hydrostatic. So each component of the delay has to be multiplied with their own type of mapping function, as you can see in the equation, last equation here. So slant total delay equals to zenith hydrostatic delay into mapping function hydrostatic plus zenith wet delay into mapping function wet. So coefficients A, B, and C, they take care about the region where the mapping function is being calculated, region as well as the time of the year. So these are dependent on specific weather conditions and a function of the latitude of the region, latitude, height, as well as day of the year. Okay, so there are different types of parameterization for mapping functions. The simplest is the Neal mapping function. It is relatively constant, easier to use, easier to compute, but it uses a larger approximation. That means it is less accurate. Okay, so in Neal mapping function, ABC coefficients are latitude, height, and day, time dependent, day of the year. While Vienna mapping function, this is more accurate. It is computed regularly on it gives a more real picture. It is computed by directly tracing the ray through the atmospheric model to generate the coefficients of the mapping function every 6 hours on the global grid. So you can see this mapping function is continuously every 6 hours it is being updated. So this will give a better picture, but this is complex as against to the Neal mapping function. So mapping function is taking care of the information at different elevation angles of the satellite. At different azimuth angles of the satellite, the information is taken care by the gradients. So you can see in the figure on the right hand side, this is the elevation direction at which mapping functions will take care of the changes in water vapor, while this is the azimuth direction, like surrounding the observer, okay, in the horizontal plane. So this information or this variation water vapor will be taken care by the gradient mapping functions. It is given by a model given by Chen and Herring. As you can see, these gradient mapping functions are dependent on both azimuth as well as elevation satellite angles. Okay, so there are two popular tropospheric models which are mainly for the modeling hydrostatic delay, but they also give some approximation for the wet delay. But it is advisable not to use these approximation. You can, if you compute hydrostatic delay using these models, directly subtract these from the total delay to get the wet delay. So as you can see, Hopfield model introduces two different characteristic heights. Okay, so different height for wet delay as well as different height for dry troposphere. Okay, so here there is an expression that assumption that there is a constant lap race of temperature. As we have already seen, there is a continuously changing vertical lapse rate of temperature in the atmosphere, which causes the different layers of the atmosphere. But here in this model, we assume that the lapse rate of temperature is constant throughout the troposphere. Also, gravity is not modeled with dependence on the height. So these two assumptions lead to finding even more accurate model, that is the Sasta-Monin model. Here you only need the pressure, surface pressure, PS, latitude information and height of the receiver. These three inputs, when you put here in this model, you get the hydrostatic delay. As against this, for computing the zenith wet delay using the Sasta-Monin model, you need surface temperature as well as water vapor pressure measured at the site. So these may not be available, these data may not be available, or accurate measurements may not be available, or even if they are available at the site, they may not represent the wet delay inside the whole atmosphere. By this statement, I mean that using the Sasta-Monin model, you can compute the zenith wet delay near the atmosphere, which is near the site. That means at lower heights. But for larger heights, like 10 kilometers till troposphere end, the zenith wet delay may not be giving a better picture when calculated using this Sasta-Monin model. You can see every input is being used is the measurements taken at the site. So naturally all the measurements are closer to whatever the picture is there at the site. We discussed about the ionosphere, what is happening. The energy, external energy from the sun is ionizing some portion of the atmosphere. Okay, so what is meant by ionizing? It is generated by the solar radiation, which dissociates and ionizes the neutral molecules and atoms. Okay, so dissociates the molecules into electrons, as free electrons as well as ions, bigger ions. Okay, so energy of the solar radiation in the visible and infrared wavelength ranges is too low to ionize the neutral gas, hence they can reach safely to the Earth's surface. Okay, here this you can see in the diagram on the right hand side, where energy from this red bar, it is being received at the surface of the earth, as against to the X, that yellow bar, as well as extreme ultraviolet UV, that blue bar. So the lengths of these bar represents the depth of penetration inside the atmosphere towards the surface of the earth. Okay, this extreme ultraviolet energy is being utilized the most in ionizing the portion of the atmosphere and creating ionospheric plasma. So what happens is the electron density will tell you or will give you the picture of refractive index as we obtained in the troposphere. So here the refractive index of the ionosphere is perceived from electron density, that is number of free electrons per unit volume. So larger the ionization happening at a particular layer, more is the electron density, and hence denser is that medium to the signal propagation. I hope you understand this. Higher ionization means larger is the refractive index for radio waves in the ionosphere. The presence of ions and free electrons decreases above 1000 kilometers. Although traces of free electrons are present up to altitudes of a few tens of thousands of kilometers in the plasmasphere or protonosphere. So this point is representing the extreme ends of the ionosphere. What is happening, this trend, the red graph that you see here, it is highest at a layer known as F2, and then it decreases towards the protonosphere, plasmasphere. Why this is happening, this decrease? Because of the low material present here to be ionized. Okay, the rarer and rarer the atmosphere gets in terms of the molecules that are available for ionization. Okay, that is why this ionization is decreasing. Electron density is decreasing as we go towards the end of the atmosphere. Okay, so because there is a difference in electron density at different layers in the atmosphere, we get the concept of layers of the ionosphere. As you can see on the right hand side lower picture, we have D region. We start with the smallest, closest to the surface of the earth, that is the D region. So it is present at the height of 60 to 90 kilometers above the surface. This is dense atmosphere. So whatever portion of atmosphere which is closer to the surface of the earth will obviously be the denser portion. So here this D sublayer is denser. So whatever ionization happens here, quick recombination of ions will also take place. So ionization level is low, electron density level is low. Okay. The level of ionization is directly related to the radiation that begins at sunrise, disappears at sunset. So what is happening? This is happening. Whatever ionization is happening, it is happening because of the energy obtained from the sun. So naturally, the densest layer will be directly proportional to the sunrise as well as energy obtained during the sunrise. And it also varies with the sun's elevation angle. So as the sun sets, the ionization will decrease. At night, some residual ionization may be less at local midnight, but this is naturally very low because it's the densest layer. Next come is the E layer. It it prevails at a height of 90 to 150 meters. It peaks around at 105 to 110 kilometers, and it is prevalent in both day and night. So at night it does not disappear. We have E region at both day and night. F region is at a height of 250 to 350 kilometers above the surface. Here electrons and ions recombine slowly due to low pressure. So this is, we are talking about the rarest layer of the atmosphere since it is farthest away from the surface of the earth. So as we go farther away from the surface of the earth, naturally the pressure will decrease because of the hydrostatic equilibrium. Hence, due to this low pressure, the recombination of electrons and ions after the ionization takes place is relatively slow. as the observable effect of the solar radiation develops more slowly peaks after noon. This separates into two layers during the day. So F region is separated into F1 and F2. Closer towards the sun is the F2 region, higher ionization, higher electron density. Okay, so F2 layer, the upper layer, is the region of the highest electron density. There is no separation between these two layers F1 and F2 during the night. But residual ionization is largest here in the F region because of slow recombination of ions and electrons. So what happens? What is the effect on the GPS signal while it propagates through the ionosphere? It speeds up the phase and slows down the PRN codes, that is CA and P codes, and the navigation method by the same amount. So we called it code delay as well as phase advancement. So it represents the same thing, ionospheric delay, but it is perceived in two different phenomena. That means the codes, the PRN codes, CA code and P code and navigation, these are slowed down by the same amount as the ionospheric delay as the code as the phase is advanced. That means this phase is reaching faster, the codes are getting slower. Okay, so although these two phenomena, they represent the same thing, that is the ionospheric delay or the ionospheric error, but it is manifesting in two different types of phenomena, as the code is delayed while the phase is advanced. By phase I mean carrier phase observable. So phase advancement and group delay are the manifestations of the ionosphere on the signal propagation. An irregular but rapid variation in the amplitude and phase is called scintillation, as you can see in the figure on the right hand side. So a disturbed or highly variant ionosphere will cause some scintillation. This can result due to diffraction. The signal can experience short-term fading by losing strength and cause phase lock problems to occur in the receiver. So phase lock, strength loss, and fading, these are the ways how the scintillations affect the signal. So how the observation data will show you that this has occurred, and there will be it will result in errors like cycle slips, phase measurement discontinuities, loss of lock, as well as position solution being off by large errors like in meters. So if position estimate, which is the main goal of the GPS, is being off by large amount of error like errors in meters, then obviously ionospheric is posing a quite a problem. So we understood what is a scintillation. Highly variant ionospheric turbulence is known as scintillation, and this is a lot of this scintillation is present near the equator. So near the equator, GPS may work in a different manner. Loss of log will occur on many satellites, and receiver would appear effectively useless. This is happening because of an anomaly known as Appleton anomaly. We will see in the next slide. So single frequency receiver can function as long as there is not much ionospheric scintillation. Rapid variation is not there, then we can use single frequency receivers. But this is not the case at the equator. We need to use the dual frequency. Okay. When many or all the satellites are affected by the disturbance, single frequency receivers are inaccurate, while dual frequency receiver will allow this error to be modeled or mitigated properly by providing multiple data sets per satellite. So we have two sets of error happening due to the two frequency or dual frequency of a receiver. Then we are able to understand, okay, this much error is happening on this frequency, this much error is happening on this frequency because of the same phenomena. Then we can use differencing operation or linear combination operation to remove or model this error, to calculate this error and just remove it from the pseudo range. Okay. We will see this in detail. The impact of GNSS signal propagation also depends on space weather. So this impact, the signal propagation through the ionosphere not only is dependent on the ionospheric condition, but also is dependent on the weather outside the atmosphere, outside the Earth's atmosphere, that is known as space weather. So if there is a solar flares are happening, some irregularities in the magnetosphere, thermosphere, exosphere, or some solar wind is happening. Okay, all these things are the manifestations inside the space weather. So any disturbance in the space weather will also affect the GNSS signal propagation. So as we spoke about an Appleton anomaly, here you can see in this figure, okay, what happens is there is a pattern of vertical distribution of electron density which is maximum at 200 to 400 kilometers, as we saw already that F layer, F subregion of the ionosphere, it is prevalent at about this much height, 200 to 400 kilometers. Why this is happening? This is due to a compromise between sufficient energy that is coming from the sun, sufficient UV and X-ray ionizing energy is coming, as well as sufficient amount of density of molecule capable of being ionized. So material भी होना चाहिए as well as the काफ़ी energy भी होनी चाहिए sufficient, so that they interact and produce the ionospheric plasma. Now this density of molecules is related to the distance from the earth, while the sufficient energy of this ionizing energy coming from outside is related to the heights, higher altitudes, okay, closer to the sun. You understand, there has to be a compromise between energy which is more prevalent at higher altitudes, while sufficient density of molecules which is more prevalent at lower heights. So there should be a balance. So this balance is achieved at a height of 200 to 400 kilometers. The parameter responsible for ionospheric delay is termed as total number of electrons, that is TEC, total electron count. Okay, this is a representation of electron density and it is a function of many variables: solar ionizing flux, magnetic activity in the region, season, time of the day, user location, and viewing direction. These are the many variables or factors which affect the total electron count at a place. So this is just like the refractivity that we understood in the troposphere. So here we account for total electron content or total electron count to understand the behavior of the signal path. between satellite and the receiver. Okay, so integral of the vertical electron density is known as total electron count. It accounts for all the electrons in a columnar cylinder of unit area. So this is just like the phenomena of precipitable water vapor that we saw in the for the troposphere. So this is the integral of vertical electron density, that is VTEC. TEC is commonly measured in TEC units. Okay, the conversion is written here. So one useful physical quantity for describing the horizontal distribution of electron component of the ionosphere is the vertical total electron content. So at different points in a horizontal plane, you compute vertical total electron count VTEC at all these different horizontal points. So different values of VTEC will be there at different points in a horizontal plane. So that is how VTEC describes the horizontal distribution of the electron content. Okay. Now what was the Appleton anomaly? The global distribution of vertical total electron count VTEC is shown or represented by the Appleton anomaly. So maxima are observed on both the sides of the geomagnetic equator that are correlated with the sun's position. So this is related to the magnetism of the earth. So peaks of electron densities are found at lower latitudes on both the sides of magnetic equators. At equator we have 0 degrees. So lower latitudes means closer to the 0 degrees. So at approximately 15° north and 15° south, these are the lower latitudes at which these peaks of electron density occur. Why do they occur? The electric field and the horizontal magnetic field interact with each other at the magnetic equator to raise the ionization to some height above the Earth's surface. Okay, when they raise, just like a fountain, and then they fall back at these two locations, lower latitudes, on both sides of the magnetic equator. This is just like a fountain of electron densities. Okay. So the largest TC values in the world typically occur at these so-called equatorial latitudes. And this phenomena is known as Appleton anomaly. In the last class, we also saw a video representing this very beautifully. So total electron count is dependent on time of the day, time of the year, space weather. That means what is happening, there is a solar peak cycle, um, solar cycle which attains peak every 11 years. So electron density levels will reach a maximum value approximately every 11 years. Okay, so some solar flare activities are happening at this peak of the solar cycle. As well as geographical location where we are measuring this total electron count. This geographical location also plays a different role. So as we saw, Appleton anomaly will obviously give highly irregular and large amounts of total electron density levels at equatorial region. Minimum will happen at the mid latitude regions. Okay. We will have a break for 10 minutes. Then I will dive into this concept of code delay and phase advancement thing. Here we from now on we will try to understand what does that mean. Okay. Let's have a break for 10 minutes. If you have any doubt up till now, just let me know. You can also use the chat box if you want. Okay, let's start. So let me introduce the concept of group and phase propagation. For plane waves traveling in x direction, the solution of wave equations that we saw that originated from the Maxwell equations, they are the equations for B and E. Okay, magnetic field B and electric field E. Okay, so the solutions of wave equations are exponential of kx minus omega t with omega and root mu epsilon equals to k, that is wave number, equals to 2 pi by lambda. Okay, so these relation we'll use here. So if we imagine a pure sinusoidal monochromatic signal traveling in the x direction, this can be described by this form: S x comma t equals to s naught cos omega t minus kx, where omega is the angular frequency, f is the frequency, wavelength is the lambda, and wave number k. This is also known as phase propagation constant. Okay, so these omega, f, and k are related by the relation shown here. Omega equals to 2 pi f. Okay, so an amplitude modulated signal can be generated by simply addition of two sinusoidal signals at slightly different frequencies. Okay, so we have a carrier in GPS, we have code signal modulated on top of the carrier signal. Okay, so there is a amplitude modulation that is happening. So this can be done by directly addition of these two equations. Okay, this general equation can be written for two different frequencies. Okay, S1 S2 equals to cos omega plus delta omega t minus k plus delta kx. Similarly, S2 xt equals to cos omega minus delta omega t minus k minus delta kx. Okay, using some trigonometric identities, we can combine these. S1 plus S2 equals to 2 cos delta omega t minus delta kx. So this is known as this portion is known as amplitude modulation, while cos omega t minus kx will represents the carrier information. So from the above equation, it follows that two signals can appear traveling at two different velocities as a result of the superposition of signals S1 and S2. So the internal oscillations here on the figure on the right hand side, you can see we are combining the first box with the second box, and then we are obtaining at the third box of figure here. So you can see some internal oscillations are happening in blue. These blue internal oscillations are represented by the phase velocity, okay, v phi, that is given by omega by k, whereas the amplitude envelope, you can see these red dots in the diagram. Okay, these are also in a wave pattern, okay, sinusoidal pattern. So these will represent the group velocity. So you can understand what is meant by group. It is grouping, it is enveloping these internal oscillations. Okay, so we have the concept of group propagation as well as phase propagation. So phase is the inside one, that smaller, what you'll say, higher frequency ones, as well as the lower frequency ones are the group propagation. This is represented by group velocity Vg, that is delta omega upon delta k. So a point on the envelope travels with the group velocity, whereas the waveform within the envelope travels with the phase velocity v phi. Okay, so in the last diagram you can see here, if you imagine a point on the outer envelope, it will look or appear as to travel with the slower velocity known as the group velocity. While if you imagine a point inside the oscillations within this envelope, this point will appear to travel with a faster velocity, that is the phase velocity. So we have the concept of group delay as well as phase advance. We will see in the next slide. Before going to the next slide, I want to show you a video to make this clear how group and phase propagation are different from each other. So you see this beat is happening. Some beat is represented. This beat is represented by the carrier or the phase velocity. So green dot is the phase velocity, pink dot or magenta dot is representing the group velocity. Pause this. Let's go back here. So I hope you understood the phenomena of two different propagations. One is traveling as a group, okay, envelope, outer envelope, and one is traveling as the inside internal oscillations in the blue. So there is a relationship between phase and group velocity. It is given by Rayleigh's equation. So phase velocity of a single electromagnetic wave propagating in the space with wavelength lambda and frequency f, okay, is given by Vp. Naturally, lambda into frequency will give this velocity. So this is the velocity of the carrier waves on the GPS signals. Okay, carrier waves means carrier phase. While for a group of waves with slightly different frequencies, okay, that we are talking about the codes on the frequency, the codes on the GPS signals. So that is the velocity of code Vg. So the propagation of the resultant energy is defined by the group velocity of the slightly different frequencies. This is given by this relation Vg equals to df by d lambda into lambda square. Now how to relate these two? This is related by taking the total differential of this equation Vp equals to lambda f. So when you take the total differential of this equation, we arrive at dVp equals to f into d lambda plus lambda into df. Okay. Now you divide this equation by d lambda. So we will get df by d lambda equals to 1 by lambda into dvp by d lambda minus f by lambda. Okay. So Vg is given by df by d lambda. You can substitute this from this total differential equation. Here you will arrive at the relation new form for the group velocity. Okay. Now you can substitute for using lambda. You can substitute the phase velocity. Here f lambda will represents the phase velocity. So this is how you obtain the Rayleigh's equation. Vg equals to Vp minus lambda into dVp by d lambda. Now there's a relationship between index of refraction n, velocity of light c, and velocity of the light in the medium. Okay. So using this relation, you can convert this equation in the refractive index form. So these two are the representations of Rayleigh's equation. So we have two concepts of velocities, phase velocity as well as group velocity. Hence, we will have two concepts of the index of refraction also. So group index of refraction as well as phase index of refraction. Okay. So ionospheric refraction and propagation delay, how they are related, using the concept of group and phase. Okay. So electromagnetic field of radio waves interacts with the charged particles whose motion is controlled by the geomagnetic field. So the degree of interaction is described by the refractive index n. So ionospheric refractive index is a function of frequency f as well as a new terminology known as plasma resonant frequency fp of the ionosphere. It is slightly different from unity, hence again we can neglect higher order of terms in F to obtain the formula for ionospheric index of refraction known as Appleton-Hartree formula, that is n equals to 1 minus n ion. N ion is the ionospheric refractivity, okay, and small n is the ionospheric index of refraction. The same thing that we did in the troposphere, capital N and small n relation. So here we have n as the index of refraction and n ion as the ionospheric refractivity. Okay, so what is this new term plasma frequency Fp? It is the resonance frequency. It is a measure of electron motion or oscillations around the heavy ions. Okay, it represents characteristic vibration frequency between the ionosphere and the electromagnetic signals. Okay, how much interaction is taking place. Okay, so this is the resonance frequency of an electron gas of density Ne excited by a radio wave. Typical values is between 10 to 20 megahertz. Okay, so when you put yes, so plasma frequency is given by this equation. Fp square equals to Ne E square by 4 pi square epsilon naught Me, and when you substitute the small e value in coulombs, electron charge as well as mass of electron and permittivity of free space, then you will arrive at the simplified value of plasma frequency Fe square 80.6 Ne. Okay, this you can use directly in your ionospheric refractivity equation. So ionospheric refractivity is given by Fp square by 2f square, now which will give us 40.3 Ne by f square. We have two frequencies f1 and f2 in GPS. So these carrier frequencies have been chosen to minimize the attenuation taking place. This is done by taking f1 and f2 quite large than the plasma frequency. Okay, if we take frequency larger than plasma frequency, then we will be able to minimize the attenuation taking place. From relationship between the group and phase velocities that we saw in the previous slide, we can arrive at the formula for group refractive index. Ng equals to n minus lambda dn by d lambda. Then some simplification is required in between, substituting all the values of refractivity and index. We will arrive at the equation group refractive index is equal to 1 plus n ion. Okay, so you understand, for phase small n is equal to 1 minus n ion, and for group it is 1 plus n ion. So here you can take the essence how group and phase propagation are different from each other. Okay, this is only the picture of refractive index. We will see how it will show in the delay, ionospheric delay. Okay, So for GPS, we associate small n with the carrier beat phase. Carrier beat phase means that um, internal oscillations that you saw in that video, and ng is associated with the pseudo range. This is represented by the um, group velocity that we saw in the previous video. Okay, so what you have to remember here, n ion's value 40.3 Ne by F square, as well as group refractive index Ng value, that is 1 plus n ion. Okay, so quantity Vg, that is group velocity, is the velocity of the modulation. Okay, in context of GPS signals, it is the velocity of the codes, P code and CA codes. Okay, so NV phase is equal to C. Similarly, NG-VG equals to C. This is the relationship between refractive index, velocity of light in a medium, as well as velocity of light in vacuum. Okay, this we already saw in previous slide, this relation below the Rayleigh's equation, n equals to C by V. Using this relation, we are writing these relationships. Small n represents for the phase multiplied by V phase equals to C. Similarly, Ng into Vg equals to C. Using this relation, as well as the group index of refraction 1 plus anion, neglecting terms of the order of anion squared or higher, the expression for phase and group velocities will become like this. So V phi is equal to C into N equals to C by 1 upon 1 minus anion. When you will normalize this, you will neglect the higher n squared terms to obtain and approximate it to C into 1 plus anion. Similarly, Vg equals to C into Ng equals to C into 1 minus anion. So these are the relation that you have to remember for phase velocity and group velocity. Since anion is the positive number, the phase velocity is larger than vacuum speed, and the group velocity is smaller than the vacuum speed by the same amount. So what is the vacuum speed? The signal that would have traveled by the velocity when there was no medium between the satellite and receiver. That is the vacuum speed, C. So the amount delta V is equal to C into anion, that is 40.3 C Ne by F square. Okay, so you understand phase velocity is larger and group velocity is smaller. The code delay or the phase advancement, these two phenomena are representations or manifestations of the ionospheric delay. These are equal in magnitude, but they are opposite in signs. Obviously, one is delay, that is, one is taking more time, while another is phase advancement, it is taking less time. It is traveling less. Realizing that ds equals to c into dt. So here in this equation, when you substitute everything, there will be that 40.3 into c, that c multiplied by ds, multiplied by dt. When you substitute all of these things, you will arrive at ionospheric delay equals to 40.3 by f square into total electron count. How this total electron count has come? Integral of Ne into ds. Okay. So this is how we arrive at ionospheric delay in units of distance. Up till now we were talking about it in terms of velocity and refractive index. Now we are talking about it in terms of distance. So the time delay is proportional to the inverse of the frequency squared. You can see here in this relation, 1 upon f square. So this is why ionosphere affects the transmissions at higher frequencies less. So less effect is happening due to ionosphere at transmissions of higher frequencies. A medium in which speed of wave is independent of frequency of wave is called non-dispersive medium. We have already spoken about this. So here we are talking about how all these things will behave if this medium was not ionosphere, if it was troposphere. So what happens in troposphere? There it is a non-dispersive medium. There is no distinction between phase velocity and group velocity. Okay. For such a medium, Vg equals to V phi as Ng is equal to N. Okay, and change in refractive index with respect to frequency is 0. Okay, so this implies for troposphere we do not need to make such distinction between group and phase propagation. This is the ionospheric delay 40.3 upon Cf square into total electron count. What are the characteristics of this delay? It is larger from lower elevation satellites. It peaks during the daytime, it subsides during the night because of the solar radiation effect. Near the geomagnetic equator poles, delays are larger. Frequency dependence is there, proportional to 1 upon f square, we saw in the formula. So this implies ionospheric delay is causing more attenuation for L2 frequency than the L1 frequency of the GPS. Delay is of the order of 5 meters, but it can reach over 150 meters under extreme solar activities. So you understand? Solar activities are related to the space weather. If there is some solar flare activities happening, some space weather disturbances happening, okay, so these can influence the delay to reach over 150 meters also, or at midday or near the horizon. Nearly 4 times greater in November. The delay is nearly 4 times greater in November when the Earth is nearing its perihelion. So perihelion means least distance from the Sun of the Earth. At this position, it is closest approach to the Sun, that it is in July near the Earth's perihelion. It is farthest point from the Sun. So you understand the distance from the Sun while orbiting the Sun also influences the ionospheric delay. The effect of ionosphere on the GPS signal usually reaches its peak in March, about time of the vernal equinox. Now, how to correct for the ionosphere error? So, as discussed before, ionospheric delay can be corrected for by using dual frequency mechanism. What is this? A secondary frequency 1.22 gigahertz specifically incorporated into the system allow users to automatically correct for the effects of range errors induced by the ionosphere. So what is the concept here? When the errors between different frequencies for a given satellite are compared with each other, how the for the same phenomena, how different frequencies are giving errors. Okay, this phenomena, when it is understood, the user can ascertain a better idea of how the ionospheric irregularities are affecting the data, and hence we can model this error. Okay, we can correct for it. So dual frequency receivers can use a linear combination of code or carrier phase in order to eliminate the ionospheric irregularities. Okay. The purpose of these frequencies, high frequencies L1 and L2, is also to penetrate the ionosphere relatively well, as the time delay caused by the ionosphere is inversely proportional to the square of frequency that we saw in the equation for delay, ionospheric delay. Okay, since the ionospheric code delay and phase advance are dependent on the frequency, it is possible to eliminate the ionospheric effects using dual frequency observation. So we saw how dependence on the frequency is there, 1 upon f square. So since there is some dependence on frequency, we can use the dual frequency observations to eliminate these effects. Okay, so how to write the pseudo ranges for L1 and L2? We have already seen these two equations before. So first is the geometric vacuum distance, that is geometric range, rho, then receiver time error, then satellite time error, then satellite code phase offset, then ionospheric P code delay at L1. Okay, so how it is written? L1, that 1 is subscript there at near I, as well as P for the P code. Then tropospheric delay, this is not dependent on frequency, hence there is no subscript of 1 or 2 here. Hardware delays and multipath effects, these are also dependent on frequency, so we have 1 written over there. Range measurement noise, this is also dependent on frequency. So these are the different errors components contained apart from the geometric distance in the pseudo range for L1 and L2. Okay, so for L2 frequency, wherever the 1 subscript was written, it will be converted to 2. Now how are we correcting for ionosphere for the pseudo range? Using simple functions of L1 and L2 frequencies, our objective is to find ionospheric free pseudo range function, that is PIF, that does not depend on the ionosphere. So these are functions of the frequencies f1 and f2, L1 and L2. Okay, so alpha f is equal to f1 upon f2 whole square, beta f is equal to f1 square upon f1 square minus f2 square. Similarly, gamma f and delta f. Okay, so these are predefined functions which, when we use in combination with the pseudo range for L1 and L2 frequencies, we will arrive at a ionospheric free pseudo range function PIF. So how to make such a linear combination? PIF is equal to beta f. We are using this function beta f into P1 minus gamma f into P2. If you try to calculate this using your notebook and pen, try to substitute these here in this equation and you will see that all the terms where 1 or 2 were coming, they are getting cancelled. Okay, so after this we will arrive at final pseudo range equation after ionospheric correction is our geometric range rho minus clock, receiver clock, satellite clock plus troposphere. Obviously it will be here because it is not dependent on frequency, plus multipath and measurement noise. These two are functions of delta 1p, delta 2p, epsilon 1p and epsilon 2p. So these are the ionospheric free combinations for multipath error as well as noise measurement noise error. Here you can see that capital TGD is also not there. So that has also been cancelled. So we arrive at a much simpler equation for pseudo range. Similarly, for carrier phase correction, these two are the carrier phase observable equations. One stands for L1 frequency and 2 stands for L2 frequency. So here, since we are writing these equations in units of cycles, we have to introduce this factor of 1 by lambda. Okay, so this is the geometric range, this is ambiguity, then this is receiver clock, this satellite clock, this is ionosphere here for 1p, this is for troposphere, and this is again for multipath as well as measurement noise. So what type of linear combination you will make? Here example is given. to arrive at an ionospheric free carrier phase function phi IF. IF stands for ionospheric free. You can multiply beta F to phi 1 minus delta F into phi 2. When you try to solve this, you can arrive at this ionospheric free carrier phase function phi IF. So here you can see geometric range portion is here, then receiver clock, then satellite clock, then ambiguity, then again ambiguity for 1 and 2, then tropospheric delay, then multipath and receiver noise. Sorry, multipath as well as measurement noise. So here you can see ionosphere term has vanished here. So this is how ionospheric free carrier phase function phi f is obtained. Now here is some disadvantage of this linear combination. It relatively has high observation noise. Okay, since some multiplication and factors are multiplied here, observation noise is relatively higher, and most important is it does not preserve the integer nature of the ambiguity parameters because multipliers beta f and delta f are not integers. So here you can see beta f multiplied by n1 and delta f multiplied by n2. N1 and N2 were integer ambiguities before, but after multiplication by these two factors, the integer nature is lost, which is not desirable. Another alternative to linear combinations for ionospheric corrections is using ionospheric delay models. So one such popular model is Klobuchar model. So what happens is it is not like if you only have this dual frequency receiver, then only you can correct for ionosphere SNEN. But you can use these type of models, empirical models, if you are using a single frequency receiver also. Okay. So first order ionospheric propagation error depends only on the electron density distributed along the ray path. Ionospheric models that describe the 3D electron density distribution around the globe as a function of time enable estimating the length-related ionospheric propagation errors. Some of the users of GPS dual frequency solution is not convenient, okay, because it is costly. So to enable point positioning for these single frequency users, GPS offers a simple ionospheric TC model for 50% corrections of single frequency measurements using 8 coefficients transmitted as part of the satellite message. So inside the satellite broadcast message only, GPS offers information about some 8 coefficients which help us to model for ionospheric error. But these corrections are only 50% accurate. But again, this can be applied for single frequency measurements. So this is the advantage as well as disadvantage of using such model. So Klobuchar model gives us the ionospheric correction algorithm, which provides a mean vertical delay at L1 frequency for given geomagnetic location and local time, and it consists of 8 parameters which are broadcast by the GPS satellites, and they allow us to predict the vertical total electron count VTEC at a given time and location in order to minimize the user computational complexity. So this is a Klobuchar model. We are modeling the diurnal variation. Diurnal means with the time of the day, how the variation is happening. The diurnal variation of the vertical ionospheric delay is simply modeled by half cosine function with varying amplitude and period depending on time and geomagnetic latitude. So you can see on the axis we have time delay with respect to local time, how this vertical ionospheric delay is changing. So this is modeled by using these 4 constants A1, A2, A3 and A4, of which A2 and A4 are of significance. We will see how. So T ion can be written as A1 plus A1 is this what you call here, offset you call, I think. So A1 plus A2 cos function half cosine 2 pi t GPS minus A3 by A4. This is the function that represents this model here. So A1 is the constant nighttime value. During night time, the vertical ionospheric delay is fixed at a constant value of 5 nanoseconds. So for night, we are assuming that there is a fixed delay is happening because not much ionization is happening at night. We are assuming a fixed value, that is the A1. A2 represents the amplitude centered at 2 o'clock local time. A3 is the constant phase shift at 2 o'clock local time, and A4 is the period of cosine function centered at 2 o'clock local time. Okay, so our interest is in A2 and A4. A2 is the amplitude and A4 is the period. So in the model, amplitude of the cosine term and its period, that is A2 and A4, are functions of geomagnetic latitude and are represented by third degree polynomials. So 8 coefficients, this is the data provided by the GPS satellite in their broadcast message itself. So 8 coefficients are updated daily by the GPS master control station, uploaded to the GPS satellites and transmitted back to the receivers via the navigation message. Okay, so these 8 coefficients you can see at bottom of the slide. A2 equals to alpha 1 plus alpha 2 phi IP plus alpha 3 phi IP square plus alpha 4 phi IP cube. So you can see this is the third degree polynomial equation where alpha 1, alpha 2, alpha 3, alpha 4 are 4 of such coefficients, and other 4 are inside the A4 equation. This is also third degree polynomial equation where beta 1, beta 2, beta 3 and beta 4. So total 8, alpha 1, alpha 2, alpha 3, alpha 4, beta 1, beta 2, beta 3, beta 4. Total 8 coefficients are there in the polynomials for A2 and A4, which are provided by the navigation message. These are used to model the ionospheric correction. So what are the inputs to the model? Geodetic latitude phi, longitude lambda, GPS time t, and azimuth and elevation of the satellite angles. The vertical time delay at the sub-ionospheric point must be multiplied by an obliquity or slant factor defined as the secant of the zenith angle at the mean ionospheric height. We will see this in later slide. So T-iono is referred to the L1 frequency. If the user requires ionospheric time delay correction on the L2 frequency, the correction term must be multiplied by a constant of 1.65. So here, using this Klobuchar model, we are arriving at ionospheric delay for the L1 frequency. For L2 frequency, we just need to multiply by a constant. What are the main assumptions here in this model? One of the most important assumption is that electron content is concentrated in a thin layer at 350 kilometers in height. So this is known as mean ionospheric height. Okay. Another assumption is that ionospheric time delay is using the geomagnetic latitude. We are not using geographic latitude. Hence, it is necessary to perform such conversion. Okay, there's a flat earth approximation so at the low and mid latitudes. Any errors in the using flat earth approximation to calculate the ionospheric intersection coordinate is small. Now, to keep away the large errors caused by the approximation at extremely high latitudes, the latitude is defined as 75 degrees even if the ionospheric latitude is calculated to be greater than 75 degrees. That means if the ionospheric intersection point, that means the point at which the signal is piercing the ionosphere, that intersection point, the latitude of such point If it is greater than 75 degrees, it is made again to the value 75 degrees. This approximation is done to keep away from large errors caused by flat earth approximation. Okay. This is reasonable because DEC is generally low at those very high latitudes. One more assumption is that this model provides 50% reduction in ionospheric error of location positioning under quiet geomagnetic conditions. So quiet geomagnetic condition means not large scintillations are happening while using this model. Okay. So this is the algorithm of the Klobuchar model, where we are starting with the earth-centered angle psi. Here in this figure you can see psi angle. Okay, first we calculate this, then we compute the latitude of the ionosphere piercing point. So you understand the ionosphere is from 50 kilometer to 1000 kilometers. कौन है? एक Hello, sorry for the interruption. So in this algorithm by Klobuchar model, uh, we are assuming the ionosphere activity to be concentrated at a mean ionospheric height known as um, mean ionospheric height of 350 kilometers, and when the signal from the GPS satellite pierces this mean height, that point is known as ionospheric pierce point, represented by this red dot, IPP. So first we will want to find the coordinates of this ionospheric pierce point. Okay. So we'll find the latitude, then we'll find the longitude, and then we'll convert this value to the geomagnetic coordinates. Okay, that is the spherical distance between geomagnetic pole to the ionospheric point. Then we'll find the local time, add this IPP. Next, that model for the vertical ionospheric delay, where amplitude and period are represented and calculated using those 8 coefficients in the broadcast navigation message. So we'll compute the amplitude using those coefficients, then we'll compute the period using those coefficients, then phase of the ionospheric delay is computed using the equation xi equals to 2 pi t minus 50400 upon pi. So period is being utilized in this equation as well as time of the IPP. Next, the slant factor is computed, achieving transition from vertical delay to the delay along the wave path. So this is again, slant factor is like a mapping function. We are converting vertical delay to the slant delay. Yeah. Then we compute finally the ionospheric time delay. Okay, so slant factor capital F, it is a function of elevation E in semicircles. Okay, this is not in radians or degrees, it is in semicircles. The slant factor is then multiplied by this amplitude and period model, and we arrive at the ionospheric time delay for L1 frequency. So this is how Klobuchar model is used for ionospheric correction algorithm. If you have any doubts, please ask. I know these are some heavy content, so you can go through these slides. I will upload these and then you can again ask me anytime. If you have any doubts right now, just ask. We will end up the session. So to summarize, ionospheric delay can be corrected using dual frequency mechanism as well as using ionospheric models like Klobuchar model. I'll quickly glide through the slides for the ionosphere. If you have any doubts, you may ask. Okay, so we will end the meeting. If you have any doubts, you may write in the chat.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.